Right now, inside every atom of your body, electrons exist in states that have persisted for billions of years without losing a single fraction of their energy. Not one bit. Classical physics says this should be impossible. A charged particle caught in the grip of an atomic nucleus should spiral inward, radiating away its energy in a fraction of a second. Every atom in the universe should have collapsed almost instantly after it formed. You shouldn't exist. The chair you're sitting in shouldn't exist. The stars shouldn't exist. Nothing made of atoms should be stable. And yet here you are, made of trillions upon trillions of atoms, every single one of them perfectly stable, their electrons holding steady in states that never run down, never need recharging, never require fuel. The electron is not a tiny battery. It doesn't slowly drain. And the reason why is one of the most profound truths physics has ever uncovered. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Everything around you right now, the screen you are looking at, the air you are breathing, the body you inhabit, all of it is made of atoms. Atoms are the foundation of everything in the physical universe. Every mountain, every ocean, every star in the sky, every cell in your body, all of it is built from atoms. And inside every single one of those atoms, there are electrons. Electrons that have been doing what they do, existing in their states, maintaining the structure of matter for billions of years. Without any fuel, without any external power source, without running down or wearing out. This seems unremarkable until you think about it carefully. Because according to the laws of physics that governed our understanding of the universe for over 200 years, this should be impossible. A charged particle caught in the grip of an atomic nucleus should radiate away its energy almost instantly. It should spiral inward and crash into the nucleus in a fraction of a second, so small you could never measure it. Every atom in the universe should have collapsed almost immediately after it formed. And that means everything made of atoms, which is everything you have ever seen, touched, or experienced, should never have existed in the first place. This is not a small problem. This is not a technicality or an edge case. This is a fundamental prediction of classical physics that says matter itself should be unstable. And yet matter is stable. You are the proof. The fact that you exist, that you are listening to these words right now, means something is deeply, profoundly wrong with the classical picture of the atom. Understanding what went wrong and what replaced it takes us to one of the most important revelations in the history of science. But to appreciate what went wrong, you first need to understand how we figured out what atoms look like on the inside. Because for most of human history, nobody had any idea. The word atom comes from the ancient Greek word atomos, meaning uncuttable. The idea was simple. If you take a piece of gold and keep cutting it in half, eventually you reach a piece so small it cannot be divided any further. That smallest piece is the atom. The ancient Greek philosopher Democritus proposed this idea around 400 BC, but it remained purely philosophical for over 2,000 years. Nobody could prove atoms existed, nobody could see them, nobody could measure them. They were an interesting idea, nothing more. It was not until the 1800s that chemistry began revealing indirect evidence for atoms. Chemists noticed that elements always combined in fixed ratios by mass. Hydrogen and oxygen always combined in the same proportions to form water. Carbon and oxygen always combined in the same proportions to form carbon dioxide. This made sense if matter consisted of discrete units with specific masses. If a water molecule always contains 2 hydrogen atoms and 1 oxygen atom, and if oxygen atoms are 16 times heavier than hydrogen atoms, you would always need 8 times more oxygen by mass than hydrogen to make water. The fixed ratios were evidence for atoms, but they were indirect evidence. Nobody had seen an atom. Nobody knew what one looked like inside. And most scientists assumed that if atoms existed, they were solid, indivisible, fundamental objects with no internal structure. Tiny, indestructible spheres. the smallest possible pieces of matter. That assumption was shattered in 1897. J. Thomson, a physicist at Cambridge University in England, was studying cathode rays. These were mysterious beams produced inside glass tubes when an electrical voltage was applied across metal plates. Nobody knew exactly what cathode rays were. Some scientists thought they were waves, some kind of disturbance rippling through the material of the tube. Others thought they were streams of particles, tiny pieces of matter being flung across the gap. The debate had been going on for decades without a definitive answer. Thomson designed experiments to settle the question once and for all. He applied electric and magnetic fields to the cathode rays and measured how they deflected. If cathode rays were waves, they should not be deflected by electric fields. Waves do not carry charge. But the cathode rays were deflected. They curved in the presence of an electric field, bending toward the positively charged plate and away from the negatively charged plate. This meant the rays carried negative charge. They were particles. And by measuring the deflection carefully, by adjusting the strength of the electric and magnetic fields, and noting how the beam responded, Thomson could calculate the ratio of charge to mass for whatever particles made up the beam. What he found stunned the scientific community. The particles in cathode rays had a negative electrical charge, and they were light. Extraordinarily light. Their mass was roughly 1/1800th the mass of a hydrogen atom, which was the lightest atom known. These particles were far smaller than any atom. Thomson had discovered something inside atoms, a subatomic particle. He called them corpuscles initially, though we now call them electrons. This was revolutionary. Atoms were not solid, indivisible spheres. They had internal parts. They contained these tiny, negatively charged electrons. But this immediately raised a question that demanded an answer. Atoms as a whole are electrically neutral. They have no net charge. If atoms contain negatively charged electrons, there must be something positively charged inside as well. Something that balances out the negative charge exactly. But what was that positive charge? And how was it arranged within the atom? Thomson proposed a model in 1904. He imagined the atom as a sphere of uniformly distributed positive charge, with electrons embedded throughout it, like raisins scattered through a pudding. This became known as the plum pudding model, named after the traditional English dessert. In Thomson's picture, the positive charge was spread evenly throughout the entire volume of the atom, and the electrons sat inside this positive cloud, held in place by electrical forces. The atom was stable because the electrons rested in equilibrium positions where the forces balanced. If an electron was nudged from its resting spot, it would oscillate back and forth around its equilibrium position, perhaps emitting light at specific frequencies as it vibrated. This seemed perfectly reasonable. It explained why atoms were neutral, because the total positive and negative charges were equal. It explained why electrons could be knocked out of atoms by sufficiently violent collisions, and it provided a coherent, detailed picture of atomic structure that scientists could calculate with and build upon. For several years, most physicists accepted the plum pudding model. It seemed to work. It was consistent with what was known at the time. There was no obvious reason to doubt it. Then Ernest Rutherford designed an experiment that changed everything. Rutherford was a New Zealand-born physicist working at the University of Manchester in England. He was one of the leading researchers in the new field of radioactivity, and he had access to alpha particles, which are particles emitted naturally by certain radioactive materials, like radium. Alpha particles are relatively heavy and energetic. Each one consists of 2 protons and 2 neutrons bound tightly together. They carry a positive electrical charge, twice the charge of a single proton, and they move fast, travelling at roughly 5% of the speed of light. Rutherford had a brilliant idea. He would use these alpha particles as probes to investigate the internal structure of atoms. He would fire them at a thin sheet of gold foil, only a few hundred atoms thick, and observe what happened when they passed through. The way the alpha particles scattered would reveal how mass and charge were distributed inside the atom. If Thomson's plum pudding model was correct, the alpha particles should pass through the gold foil with only slight deflections. Think about it. In the plum pudding model, the positive charge is spread out uniformly throughout the entire volume of the atom. It is diffuse, thin, like a fog. An alpha particle ploughing through this fog would experience only gentle, distributed forces. It might be nudged slightly off course, deflected by a degree or two, but it should pass through without much trouble. The force would never be concentrated enough to cause a sharp deflection. It would be like throwing a heavy bowling ball through a large cloud of cotton candy. The cotton candy offers some slight resistance, but it cannot stop the bowling ball. It certainly cannot bounce it backward. The bowling ball ploughs through with barely a change in direction. Rutherford assigned the experiment to two of his researchers, Hans Geiger and Ernest Marsden. They set up the apparatus carefully. A radioactive source emitted alpha particles in a controlled beam. The particles struck a thin gold foil at a known angle. Surrounding the foil at various positions were small screens coated with zinc sulfide, a material that produces a tiny flash of light when struck by an alpha particle. By sitting in a darkened room and counting flashes at different angles around the foil, Geiger and Marsden could determine how many alpha particles were scattered in each direction. They started collecting data. Most of the alpha particles did exactly what the plum pudding model predicted. They passed straight through the gold foil with little or no deflection. This made sense. If the atom is a diffuse cloud of charge, most of it is easy to pass through. But then Geiger and Marsden noticed something extraordinary. A small fraction of the alpha particles were deflected at very large angles. Some bounced back at angles greater than 90 degrees. A few came almost straight back toward the source, deflected by nearly 180 degrees, reversing direction almost completely. About one alpha particle in every 8,000 was deflected by more than 90 degrees. This was astonishing, completely unexpected. Rutherford later described his reaction with a vivid analogy. He said it was as if you fired a 15-inch artillery shell at a piece of tissue paper, and the shell came back and hit you. In everyday experience, nothing like that happens. A heavy, fast-moving projectile does not bounce backward off a thin, diffuse target. The plum pudding model could not explain this result. A uniform cloud of positive charge simply cannot exert enough concentrated force to reverse the direction of a fast, heavy alpha particle. There is no mechanism for it. The force would be too spread out, too diluted across the entire volume of the atom. It would be like trying to stop a cannonball by throwing a handful of dust at it. Rutherford spent months analysing the data. He worked through the mathematics of how a charged particle would scatter off different distributions of charge. He tested various arrangements. Could a uniform sphere produce large angle deflections? No, the math showed it could not. Could multiple small deflections add up to a large total deflection? He calculated the probabilities and found they were far too small to explain how many alpha particles bounced back. The only explanation that fit the data was that the positive charge and nearly all the mass of the atom were concentrated in an incredibly tiny, incredibly dense region at the very center. In 1911, Rutherford published his conclusion. The atom had a nucleus. This central region contained all the positive charge and almost all the mass, packed into a space roughly 100,000 times smaller than the atom itself. The rest of the atom was empty space, vast compared to the nucleus, with electrons somewhere out at the edges, held by electrical attraction but orbiting at enormous relative distances. Think about what this means for a moment. If you could scale an atom up to the size of a football stadium, the nucleus would be about the size of a small marble sitting at the 50-yard line. Everything else, the entire volume of the stadium, the seats, the concourses, the sky above, would be empty space. The atom is almost entirely nothing, a tiny speck of concentrated mass and charge at the center, surrounded by a vast emptiness in which a few electrons exist at distances that are enormous compared to the size of the nucleus. When most alpha particles passed through the gold foil in Rutherford's experiment, they were sailing through this immense emptiness, never coming close to any nucleus. But occasionally, by pure chance, an alpha particle happened to fly directly toward a nucleus, and when it did, it encountered all of that concentrated positive charge in a space 100,000 times smaller than the atom. The electrical repulsion was enormous, a focused, intense force that could stop the alpha particle and send it ricocheting backward. Rutherford's discovery gave us the nuclear model of the atom, a tiny, dense, positively charged nucleus at the center, surrounded by negatively charged electrons at relatively vast distances. It was an extraordinary achievement. It overturned the plum pudding model completely. It revealed that the internal structure of the atom was far stranger and far emptier than anyone had imagined. But it also created a crisis. A devastating, fundamental crisis that threatened to undermine the entire framework of classical physics. Here is the problem. Rutherford's model looks like a miniature solar system, electrons circling a nucleus, like planets orbiting a star. This picture is intuitive and appealing. People can visualize it easily. But it is also fatally flawed. And the flaw comes from one of the most well-established and thoroughly tested theories in all of physics: the theory of electrodynamics. The theory of electricity, magnetism, and light, developed primarily by James Clerk Maxwell and published in the 1860s. Maxwell's equations are among the greatest achievements in the history of science. They unified electricity and magnetism into a single, coherent framework. They predicted the existence of electromagnetic waves, ripples in the electric and magnetic fields that propagate through space at a definite speed. And Maxwell calculated that speed. It turned out to be the speed of light. Light itself is an electromagnetic wave. Maxwell had unified not just electricity and magnetism, but optics as well. Three branches of physics previously thought to be separate turned out to be aspects of a single underlying phenomenon. This was confirmed experimentally by Heinrich Hertz in the late 1880s, when he generated and detected electromagnetic waves in his laboratory, exactly as Maxwell's equations predicted. By the time Rutherford discovered the nucleus, Maxwell's equations had been tested and confirmed by countless experiments over nearly half a century. They were considered bedrock. And one of the things Maxwell's equations tell us, unambiguously and without exception, is that any electric charge that accelerates must radiate electromagnetic energy. This is not optional. It is not a suggestion or an approximation. It is a rigorous mathematical consequence of the theory, confirmed by every experiment ever conducted on accelerating charges at everyday scales. When you accelerate a charged particle, the electromagnetic field around it rearranges itself. That rearrangement cannot happen instantaneously everywhere. It propagates outward at the speed of light as an electromagnetic wave. Energy is carried away from the charge by that wave. The accelerating charge loses energy. The amount of energy it loses per second depends on how hard it is accelerating. The greater the acceleration, the more intensely it radiates. This happens everywhere in technology and nature. Radio antennas work by accelerating electrons back and forth along a metal wire. The accelerating electrons radiate electromagnetic waves outward in all directions. That radiation is the radio signal your receiver picks up. Synchrotron light sources, used in scientific laboratories around the world, accelerate charged particles along curved paths at nearly the speed of light. The particles radiate so intensely that the emitted light, called synchrotron radiation, is bright enough to study the atomic structure of materials. When a fast-moving charged particle passes close to an atomic nucleus and is deflected by its electric field, the deceleration causes the particle to radiate. This is called Bremsstrahlung, a German word meaning breaking radiation, and it is how X-ray machines in hospitals work. The principle is always the same. Accelerating charges radiate electromagnetic energy. This is one of the most thoroughly tested facts in all of physics. Now apply this to Rutherford's atom, an electron orbiting a nucleus. An orbit is a curved path. To follow a curved path, the electron must constantly change direction. Changing direction means changing velocity. Changing velocity, even if the speed stays the same, means the electron is accelerating. This is centripetal acceleration, the same kind of acceleration that keeps a ball on a string moving in a circle. The ball on the string is constantly accelerating toward the center of the circle, even though its speed along the path may be perfectly constant. Its velocity is changing because its direction is changing, and acceleration is any change in velocity, whether that change is in speed, direction, or both. So, according to classical physics, an electron orbiting a nucleus is an accelerating charge. And Maxwell's equations say, without any ambiguity, without any loophole, that an accelerating charge must radiate electromagnetic energy. The electron must emit electromagnetic waves continuously as it orbits. Not occasionally, not under special conditions, continuously, every moment it is in that curved orbit. But here is the devastating consequence. If the electron is radiating energy, it is losing energy. Energy does not appear from nowhere. The energy carried away by the electromagnetic waves must come from somewhere, and it comes from the electron's kinetic and potential energy. If the electron loses energy, its orbit must shrink. It no longer has enough energy to maintain its distance from the nucleus, so it falls closer. But as it spirals closer, the electrical force pulling it toward the positively charged nucleus gets stronger, because the force increases as the distance decreases. A stronger pull means tighter curvature. Tighter curvature means greater acceleration. Greater acceleration means more intense radiation. More radiation means faster energy loss, which means the electron spirals inward even faster. The process feeds on itself. It is a runaway collapse, accelerating as it goes, like a ball rolling downhill on a slope that gets steeper and steeper. Physicists calculated how long this collapse would take using the well-known Lama formula, which gives the power radiated by an accelerating charge. They plugged in the charge of the electron, its mass, the strength of the electrical attraction to a hydrogen nucleus, the initial orbital radius. And they got an answer. The electron would spiral from a typical atomic orbit all the way into the nucleus in roughly 16 trillionths of a second. Not 16 seconds, not 16 milliseconds, not 16 millionths of a second. 16 trillionths. That is approximately 1.6 times 10 to the negative 11 seconds. To put that in perspective, in one single second, this collapse could happen over 60 billion times. In the time it takes you to blink your eye, about 300 milliseconds, the collapse could have happened nearly 20 billion times over. For all practical purposes, the collapse is instantaneous. This means that, according to classical physics, every atom in the universe should have collapsed almost the instant it formed. Every electron should have spiraled into its nucleus, releasing a brief chirp of electromagnetic radiation as it fell, the frequency increasing rapidly as the orbit shrank and the electron accelerated faster and faster. After less than 100 trillionths of a second, the electron would have reached the nucleus. The atom would be gone. Not gone in the sense of being destroyed by some external force, gone in the sense of being inherently, fundamentally unstable, incapable of existing for any meaningful length of time. And if atoms are not stable, then nothing made of atoms is stable. No molecules, because molecules are made of atoms bonded together. No crystals, no metals, no rocks, no water. No proteins, no cells, no DNA. No stars, because stars are made of atoms compressed by gravity. No planets, because planets are made of atoms held together by gravity and chemical bonds. No you, because you are made of atoms, roughly 7 billion of them, every single one of which should have collapsed before you ever had a chance to form. The entire material universe, everything made of ordinary matter, depends absolutely on atoms being stable. If electrons spiral into nuclei in trillionths of a second, then chemistry is impossible. Biology is impossible. Solid matter is impossible. The ground beneath your feet should not hold together. The air in your lungs should not exist as molecules. Your own body should dissolve into a formless soup of bare nuclei and radiation. And yet, here you are, sitting comfortably in a universe made of perfectly stable atoms. Atoms that have existed for billions of years. Atoms whose electrons show absolutely no sign of spiraling inward, no sign of radiating away their energy, no sign of collapsing. Atoms that are, by every measurement we have ever made, completely and utterly stable. This was the crisis. Not a minor discrepancy, not a small gap between theory and observation that could be patched with a clever correction or a new constant plugged into an equation. This was a total, catastrophic failure of classical physics to explain the most basic fact about the material world. Matter exists. Atoms are stable. And classical physics, using its most trusted and thoroughly tested laws, predicts that they should not be. Let me be very clear about what made this so deeply disturbing. It was not that physicists had made an error somewhere. The mathematics was correct. Maxwell's equations were correct and had been confirmed by decades of experiments. The prediction that accelerating charges radiate was correct and directly observable in every antenna, every synchrotron, every X-ray tube. Rutherford's nuclear model of the atom was correct. The experimental evidence for a tiny, dense nucleus surrounded by distant electrons was overwhelming and had been independently confirmed by multiple laboratories. Every individual piece of the argument was solid. Every step in the reasoning was logically sound, built on laws that had been tested and proven. And the conclusion was that atoms should be unstable. The problem was not with the logic or the math. The problem was with an assumption so deep, so fundamental, so seemingly obvious that most physicists did not even realize they were making it. The assumption was that electrons inside atoms behave the same way as charged objects in the everyday world. That an electron circling a nucleus is essentially the same kind of thing as a charged ball swinging in a circle on a string, or an electron being pushed back and forth in a radio antenna, just on a much smaller scale. That the physics governing the very small is simply a miniaturized version of the physics governing the everyday. This assumption seems perfectly reasonable. It seems like obvious common sense. Why would the laws of physics change just because you make things smaller? A baseball follows Newton's laws of motion. A marble follows the same laws. A grain of sand follows the same laws. An object the size of a bacterium follows the same laws. Why would an electron be any different? Surely the rules of the game remain the same, regardless of the size of the players. But this is precisely where classical physics went wrong. The assumption that you can simply shrink everyday physics down to atomic scales and have it still work is not just slightly off. It is fundamentally, profoundly, spectacularly incorrect. The behavior of electrons inside atoms is nothing like the behavior of any charged object you have ever encountered in your everyday life. The rules change completely at the atomic scale. Not subtly, not by small corrections, completely. The electron in an atom does not orbit the nucleus like a planet orbits a star. It does not trace out a neat, curved path through space. It does not have a precise position and velocity at each moment in time, the way a planet does. It does not accelerate in the classical sense. And because it does not accelerate in the classical sense, it does not radiate in the way Maxwell's equations predict for an accelerating classical charge. The classical rule about accelerating charges radiating is not wrong. It works perfectly for antennas and synchrotrons and X-ray tubes and every other macroscopic system. But it does not apply to electrons in atoms, because electrons in atoms are not doing what the classical picture imagines them doing. The resolution to this crisis required something that no one in the early 1900s could have anticipated: a completely new framework for understanding the physical world. A framework that would overturn assumptions about the nature of reality that had been taken for granted for centuries. A framework so strange, so counterintuitive, so radically different from everyday human experience that many of the greatest physicists of the era struggled to accept it, even after the evidence became overwhelming. Classical physics was not wrong in any general sense. It works beautifully for baseballs, planets, bridges, radio towers, and everything else at human scales and above. It describes the everyday world with extraordinary precision, but it does not describe atoms. At the atomic scale, a completely different set of rules governs reality, and those rules explain something that classical physics never could: why electrons do not spiral into nuclei, why atoms are stable, why matter holds together, why you exist. The crisis was real. Classical physics, using its most trusted and experimentally verified laws, predicted that every atom in the universe should collapse in a fraction of a trillionth of a second. Electrons should spiral into nuclei, matter should disintegrate, and nothing we see around us should exist. And yet, atoms are stable. Matter holds together. The universe is filled with structures built from atoms that have persisted for billions of years without showing any sign of collapse. Something fundamental had to give. Some assumption buried so deep in the foundations of classical physics that no one had questioned it had to be wrong. And in the early 1900s, a series of physicists began to realize what that assumption was. They discovered that the behavior of electrons inside atoms follows an entirely different set of rules than anything classical physics had ever imagined. Rules so strange, so alien to everyday intuition, that they overturned centuries of thinking about the nature of reality. This is the story of how we learned what electrons actually do inside atoms. And it begins with a physicist who was willing to make a guess so bold that even he did not fully believe it at first. In 1913, a young Danish physicist named Niels Bohr proposed something radical. He had studied Rutherford's nuclear model of the atom. He understood the crisis perfectly. He knew that an electron orbiting a nucleus in a classical orbit would radiate away its energy and collapse. And rather than trying to patch the problem with small adjustments, Bohr did something audacious. He simply declared, by postulate, that certain special orbits were exempt from this rule. He said that electrons in atoms could exist in specific orbits without radiating. These were stable orbits, allowed orbits. As long as the electron remained in one of these allowed orbits, it would not emit any electromagnetic radiation, regardless of what classical physics said it should do. This was not a derivation. Bohr did not prove this from deeper principles. He simply stated it as a rule and then explored the consequences. But Bohr went further. He did not just say certain orbits were allowed, he specified which ones. He proposed that the allowed orbits were determined by a quantization condition. The angular momentum of the electron in its orbit could only take on specific discrete values, whole number multiples of a fundamental constant divided by 2 pi. That fundamental constant was Planck's constant, the same constant Max Planck had introduced in 1900 to solve an unrelated problem involving the radiation emitted by hot objects. Planck's constant had appeared in the physics of light and energy. Now Bohr was using it to restrict the behavior of electrons inside atoms. The quantization condition meant that only certain orbits were possible, not a continuous range of distances from the nucleus, but a specific set. Orbit number 1, the smallest and closest to the nucleus. Orbit number 2, farther out. Orbit number 3, farther still. Each orbit had a specific radius and a specific energy. The electron could be in any one of these allowed orbits, but it could not exist between them. There were no in-between distances, no gradual sliding from one orbit to another. The electron was either in orbit 1, or orbit 2, or orbit 3, and nothing in between was permitted. This was a stunning break from classical physics. In classical physics, orbits can have any radius. A planet orbiting a star can be at any distance. There is no rule saying the planet must orbit at exactly this radius and no other. The possible orbits form a continuous range. But Bohr was saying that at the atomic scale, this continuity breaks down. Only certain discrete values are allowed. The possible orbits are like rungs on a ladder. You can stand on the first rung, the second rung, the third rung, but you cannot stand between rungs. The rungs are all there is. Bohr then calculated the energies of these allowed orbits for the simplest atom, hydrogen, which has just one proton in its nucleus and one electron. The results were remarkable. The energies he calculated matched, with impressive precision, the experimentally observed spectral lines of hydrogen. For decades, scientists had known that when hydrogen gas is heated or electrified, it emits light at very specific colours, very specific wavelengths. Not a continuous rainbow of every colour, but a handful of distinct, sharp lines. A Swiss mathematician named Balmer had discovered in 1885 that the wavelengths of hydrogen's visible spectral lines followed a simple mathematical pattern, but nobody understood why. It was a formula without a theory, a pattern without an explanation. Bohr's model provided the explanation. Each spectral line corresponded to an electron jumping from a higher energy orbit to a lower energy orbit. When the electron made this jump, the energy difference between the two orbits was released as a single particle of light, a photon, with a very specific wavelength. Different jumps produced different energy differences, which produced different wavelengths. The sharp spectral lines were not mysterious. They were the signatures of electrons making transitions between quantized energy levels. The Balmer pattern emerged naturally from Bohr's quantization condition. It was a triumph. But Bohr's model had problems, serious problems. It worked beautifully for hydrogen, the simplest atom with a single electron, but it struggled with heavier atoms that had multiple electrons. It could not explain the fine details of spectral lines observed with high-precision instruments. It could not explain why some spectral lines were brighter than others. And most fundamentally, it was a strange hybrid. It used classical mechanics to describe the electron's motion in its orbit, classical orbits with definite positions and velocities, but then grafted on the quantum condition by fiat, simply declaring that certain orbits were allowed and that radiation did not occur in those orbits without explaining why. Why should certain orbits be exempt from the laws of electrodynamics? Why should angular momentum be quantized? These were not small questions. Bohr's model gave correct answers for hydrogen, but it could not explain its own assumptions. It was a signpost pointing in the right direction, but it was not the destination. The true understanding required a much deeper revolution in thinking. And that revolution began with a simple but profound question asked by a French physicist in 1924. Louis de Broglie was a doctoral student in Paris when he proposed an idea that earned him a Nobel Prize and changed the course of physics. His idea was this: if light, which everyone had always thought of as a wave, could also behave as a particle, as Einstein had shown with the photoelectric effect in 1905, then perhaps matter, which everyone had always thought of as particles, could also behave as a wave. Perhaps the electron was not just a tiny charged ball. Perhaps it also had a wave nature. And perhaps that wave nature was the key to understanding why only certain orbits were allowed in Bohr's model. De Broglie proposed a simple formula relating the wavelength of a particle's associated wave to its momentum. Higher momentum meant shorter wavelength. Lower momentum meant longer wavelength. Every particle, every electron, every proton, every atom, every object in the universe had an associated wavelength. For large objects like baseballs and planets, the wavelength is so incredibly tiny that it is completely undetectable. The wave nature of a baseball is real in principle, but the wavelength is billions of times smaller than an atomic nucleus. It has absolutely no practical effect on the baseball's behavior. At everyday scales, the wave nature of matter is invisible, which is why nobody noticed it for all of human history. But for electrons inside atoms, the situation is completely different. An electron is so light and its momentum so small that its de Broglie wavelength is comparable to the size of the atom itself. At atomic scales, the wave nature of the electron is not a negligible curiosity. It dominates the electron's behavior. The electron is not a tiny ball tracing a circular path around the nucleus. It is a wave. And waves behave fundamentally differently from particles. Here is where the crucial insight comes in. Think about a guitar string. When you pluck a guitar string, it vibrates, but it does not vibrate at just any frequency. The string is anchored at both ends, and this constraint limits which vibration patterns are possible. Only certain wavelengths fit on the string. The longest wavelength that fits is twice the string's length. That is the fundamental mode, the lowest note the string can produce. The next allowed wavelength is exactly the string's length. That is the second harmonic. Then 2/3 the string's length, 1/2 the string's length, and so on. Each allowed wavelength is a whole number fraction of a specific length determined by the string's physical constraints. These allowed vibration patterns are called standing waves. They are called standing because the pattern does not travel along the string. Instead, the string vibrates in place, with fixed points called nodes that do not move, and points between the nodes that oscillate up and down. Standing waves are stable. They persist. They do not radiate away their energy the way a traveling wave does, because they are not going anywhere. They are just vibrating in place, maintaining their pattern. The key thing is that only specific wavelengths produce standing waves. If you try to create a vibration with a wavelength that does not fit the string's constraints, the wave interferes with itself destructively. The peaks of one cycle overlap with the troughs of another, and they cancel out. The vibration dies away. It cannot sustain itself. Only wavelengths that fit perfectly, where the wave wraps around and reinforces itself constructively, survive as stable, standing patterns. Now apply this to an electron wave in an atom. De Broglie realized that if the electron has a wave nature, and if that wave wraps around the nucleus, then only certain wavelengths will fit. Imagine the electron wave circling the nucleus. For the wave to be stable, it must close on itself smoothly. The wave must come back around and match up perfectly with where it started. If it does not match up, the wave interferes with itself destructively and cancels out. Only wavelengths where a whole number of complete cycles fit around the circumference of the orbit produce stable, self-reinforcing patterns. This is exactly Bohr's quantization condition, but now it has a physical explanation. The allowed orbits are not arbitrary. They are the orbits where the electron's wave fits perfectly, forming a standing wave pattern around the nucleus. One complete wavelength around the circumference gives the first allowed orbit. 2 complete wavelengths give the second. 3 give the third, and so on. The orbits are quantized because only certain wavelengths produce standing waves, just like only certain wavelengths produce standing waves on a guitar string. The quantum condition is not a mysterious rule imposed from the outside. It emerges naturally from the wave nature of the electron. And here is the crucial point for our story. A standing wave does not radiate energy. A guitar string vibrating in a standing wave pattern does not send energy traveling off the string into space. The energy stays in the vibration. The pattern sustains itself. Similarly, an electron in a standing wave pattern around a nucleus does not radiate electromagnetic energy. The wave is stable. It is stationary. It is not accelerating in the classical sense because it is not a particle tracing a path. It is a wave pattern that simply exists, vibrating in place, stable and persistent. This is why the electron does not spiral into the nucleus. It is not a tiny charged ball orbiting like a planet. It is a wave, and that wave forms a standing pattern around the nucleus that is inherently stable. The classical prediction of collapse was based on treating the electron as a classical charged particle following a classical orbit. But the electron is not classical. It is quantum. And quantum waves in stationary states do not radiate. De Broglie's idea was bold and beautiful, but it was still theoretical. A hypothesis, however elegant, is not a fact until nature confirms it. That confirmation came in 1927, and it came in a way that left absolutely no room for doubt. Clinton Davison and Lester Germer, 2 physicists working at Bell Labs in the United States, were studying how electrons bounced off the surface of a nickel crystal. They were not trying to prove de Broglie right. They were doing materials science, investigating the structure of metal surfaces. But during one experiment, an accident occurred. Their vacuum chamber broke, exposing the nickel target to air. The nickel oxidized. To repair the damage, they heated the nickel to high temperature to drive off the oxygen. What they did not realize was that the heating process changed the nickel from a jumble of tiny, randomly oriented crystals into a few large crystals with a regular, repeating atomic lattice. When they resumed their experiment, firing electrons at this newly crystallized nickel surface, the results were completely different from before. Instead of scattering in a relatively smooth pattern, the electrons came off the surface in sharply defined beams at very specific angles. Davison and Germer recognized what they were seeing. It was a diffraction pattern. The electrons were behaving exactly like waves hitting a regular lattice and diffracting, their waves bending around the rows of atoms and interfering constructively at some angles and destructively at others, producing bright spots where the waves reinforced and dark gaps where they cancelled. This was something only waves could do. Particles cannot diffract. If you throw tiny balls at a lattice, they bounce off in all directions without creating a pattern of bright and dark bands. Only waves produce diffraction patterns, because only waves interfere constructively and destructively. Davison and Germer measured the angles carefully. They calculated the wavelength implied by the diffraction pattern, and it matched de Broglie's prediction precisely. The electrons had exactly the wavelength that de Broglie's formula said they should have, given their momentum. Electrons were waves. Not metaphorically, not approximately. Electrons genuinely had wave properties, measurable and observable, confirmed by the same kind of diffraction pattern that had been used for over a century to prove that light is a wave. The electron, that tiny charged particle discovered by Thomson in 1897, was also a wave. Both descriptions were true simultaneously. This dual nature, particle and wave at the same time, was not a contradiction. It was the fundamental character of quantum objects. But the standing wave picture, while a powerful insight, was still incomplete. It was still rooted in the idea of orbits, of waves traveling around well-defined circular paths. The true quantum mechanical description goes much deeper, and it arrived in 1925 and 1926 with the work of several physicists, most notably the Austrian physicist Erwin Schrödinger. Schrödinger developed a mathematical equation that describes how the wave associated with a particle evolves and behaves. This equation, now known simply as the Schrödinger equation, is to quantum mechanics what Newton's second law is to classical mechanics. It is the fundamental equation of motion, but instead of telling you the position and velocity of a particle at each moment in time, it tells you something completely different. It tells you the wave function. The wave function, usually represented by the Greek letter psi, is a mathematical object that encodes everything there is to know about the quantum state of the particle. It is a function that has a value at every point in space, and those values change over time according to the Schrödinger equation. What does the wave function mean physically? This is where quantum mechanics becomes truly strange. The wave function does not tell you where the electron is. It tells you the probability of finding the electron at each location if you were to look for it. More precisely, the square of the wave function at any point gives the probability density at that point. Where the wave function is large, the electron is more likely to be found. Where the wave function is small, the electron is less likely to be found. Where the wave function is zero, the electron will never be found. This is profoundly different from classical physics. In classical physics, a particle has a definite position at every moment. It is here, at this exact point in space, right now. You might not know where it is, but that is your ignorance. The particle itself knows where it is. It has a definite location whether you look at it or not. In quantum mechanics, this is not the case. Before you measure the electron's position, it does not have a definite position. It exists in a spread-out state described by the wave function. The electron is not at any particular point. It is smeared out across space, existing in a superposition of all possible locations with different probabilities. When Schrödinger applied his equation to the hydrogen atom, something extraordinary emerged. He solved for the wave functions of an electron bound to a proton by the electrical attraction between them, and the solutions were not arbitrary. Just like standing waves on a guitar string, only certain solutions existed. The equation had solutions only for specific, discrete values of energy. These were the allowed energy levels. The same energy levels Bohr had postulated, but now derived from first principles, from a fundamental equation of physics, without any arbitrary assumptions or ad hoc rules. The allowed energy levels emerged naturally from the mathematics of the Schrödinger equation, just as the allowed standing wave patterns on a guitar string emerged naturally from the physics of vibrating strings. The quantization was not imposed. It was a consequence of the equation and the boundary conditions. The wave function must be well behaved. It cannot blow up to infinity anywhere. It must be normalizable, meaning the total probability of finding the electron somewhere must add up to 100%. These mathematical requirements restrict the solutions to a discrete set. Only certain energies are possible. Each solution, each allowed energy level, corresponds to a specific wave function with a specific shape. These shapes are what we call atomic orbitals. They are not orbits. An orbit implies a path, a trajectory, a moving particle. An orbital is a probability distribution, a cloud, a map showing where the electron is likely to be found. The lowest energy state, the ground state, has a wave function that is perfectly spherical. If you could somehow make the probability cloud visible, it would look like a soft, fuzzy ball centered on the nucleus. The cloud is densest near the center, meaning the electron is most likely to be found relatively close to the nucleus, and it fades gradually at larger distances, thinning out further and further without ever reaching a hard edge. There is no sharp boundary where the atom ends and empty space begins. The probability just gets smaller and smaller the farther out you go, approaching zero but never quite reaching it. The electron could, in principle, be found very far from the nucleus. It is just extremely unlikely. Think of it like fog. Near the center of a fog bank, the fog is thick and dense. As you move outward, it thins, becoming wispy and faint. There is no wall of fog, no hard boundary. It simply fades. The electron's probability cloud fades the same way. Higher energy states have more complex shapes that look nothing like circular orbits. The second energy level includes a spherical shape with a larger radius, but also a dumbbell shape, two lobes of high probability pointing in opposite directions away from the nucleus, with a thin zone of zero probability between them. That zero probability surface is a node. The electron will never be found on that surface. It might be found in either lobe, but never at the node between them. Higher energy levels produce even stranger shapes. Some look like four-lobed clovers, others resemble donuts wrapped around dumbbells. Some have multiple concentric shells of probability, separated by spherical nodes, where the probability drops to exactly zero, like the layers of an onion with gaps between them. These shapes are not artistic metaphors. They are precise mathematical functions, calculated from the Schrödinger equation, confirmed by countless experiments. When chemists talk about the shapes of molecules, about why water is bent and carbon dioxide is linear, about why diamond is hard and graphite is soft, they are talking about these orbital shapes. The shapes determine how atoms bond, how molecules form, how matter behaves. Chemistry itself is the study of what happens when these probability clouds overlap and interact. The existence of nodes is one of the clearest signatures that the electron is a wave. Only waves have nodes. When a guitar string vibrates in its second harmonic, the center of the string does not move. That is a node. The string vibrates on either side of that node, but the node itself is perfectly still. Electron wave functions have nodes for exactly the same reason. They are standing wave patterns, and standing waves always have nodes. The more nodes in the pattern, the higher the energy, just like higher harmonics on a guitar string have more nodes and higher pitch. Now here is the essential point. These quantum states are stationary. That word has a precise technical meaning in quantum mechanics. A stationary state is one in which the probability distribution does not change with time. The wave function itself has a time-dependent phase factor, a mathematical oscillation, but the physically observable quantity, the probability of finding the electron at each point, remains constant. Nothing is changing. Nothing is moving in the classical sense. The electron is not going anywhere. It is simply existing in a stable quantum state whose probability distribution is frozen in time. And because nothing is accelerating, nothing is radiating. The classical disaster, the prediction that the electron should continuously emit electromagnetic radiation and spiral inward, was based on treating the electron as a classical charged particle following a classical orbit. But in quantum mechanics, the electron is not following an orbit. It is in a stationary state. Its probability distribution does not change. There is no classical acceleration. There is no changing direction of motion, because there is no well-defined direction of motion to change. The electron does not have a trajectory. It has a wave function. And the wave function of a stationary state, by definition, does not evolve in any way that would produce radiation. This is the resolution to the crisis. The electron in an atom does not behave like a tiny planet circling a nucleus. It does not trace a curved path through space. It does not accelerate in the classical sense. It exists as a quantum mechanical wave function, a spread-out probability cloud described by the Schrödinger equation. The allowed states are standing wave patterns, analogous to the standing waves on a guitar string, but in 3 dimensions, and governed by the electrical attraction to the nucleus. These states are inherently stable. They persist indefinitely without radiating energy, without decaying, without the electrons spiraling inward. The atom does not collapse because the electron is simply not doing what classical physics assumed it was doing. It is worth pausing to appreciate how radical this is. For centuries, physics was built on the idea that you can, in principle, track exactly where every particle is and exactly how it is moving at every moment. This idea, called determinism, was the philosophical foundation of classical physics. If you know the position and velocity of every particle in the universe at one moment, you can, in principle, calculate the entire future and the entire past. The universe is a clockwork mechanism, and physics is the study of the gears. Quantum mechanics dismantles this picture entirely. The electron in an atom does not have a definite position. It does not have a definite velocity. It does not trace a definite path. These concepts, so fundamental to classical physics, simply do not apply. The electron has a wave function, and the wave function gives you probabilities, not certainties. You can ask the question, if I measure the position of the electron right now, what are the chances I will find it in this region of space? And quantum mechanics gives you a precise answer to that question. But you cannot ask the question, where exactly is the electron right now? Because that question has no answer. The electron does not have an exact position until you measure it. Before measurement, it exists in a superposition of possibilities. This means the mental picture most people have of the atom, the picture of little balls orbiting a central cluster like a miniature solar system, is wrong. Not slightly wrong, not approximately wrong, but fundamentally wrong. Electrons do not orbit nuclei. They occupy quantum states, stationary states, standing wave patterns, probability clouds. And these states are stable, inherently, intrinsically, quantum mechanically stable. Now, this might raise a question. If the electron in a quantum state is not moving, if the probability distribution does not change with time, then what is the electron doing? Is it just sitting there motionless? Not exactly. The electron still has kinetic energy. It still has momentum, or more precisely, a distribution of possible momenta. The uncertainty principle guarantees that if the electron is confined to a small region of space, near a nucleus, its momentum cannot be zero. It must have some kinetic energy. But this is quantum kinetic energy. It is not the kinetic energy of a ball rolling along a path. It is the kinetic energy associated with the spatial structure of the wave function. A wave function that varies rapidly in space corresponds to higher kinetic energy. One that varies slowly corresponds to lower kinetic energy. The electron in an atom has kinetic energy because its wave function has spatial structure, not because it is moving along a trajectory. This is a subtle and important distinction. In classical physics, kinetic energy comes from motion. Something moves, it has kinetic energy. In quantum mechanics, kinetic energy comes from the shape of the wave function. The more the wave function varies from point to point, the higher the kinetic energy. An electron confined near a nucleus has a wave function that is concentrated in a small region, and concentration means rapid spatial variation, which means significant kinetic energy. But this energy is not the result of classical motion. No trajectory is involved, no orbit, no acceleration. Just the intrinsic quantum property of a wave function existing in a confined space. And because there is no classical acceleration, there is no classical radiation. Maxwell's equations tell us that accelerating charges radiate. That rule still holds. It has not been repealed. But it requires actual classical acceleration, an actual change in velocity of an actual charged particle following an actual trajectory. An electron in a quantum stationary state is not doing any of that. It has no trajectory. It has no velocity in the classical sense. It is not accelerating. So there is nothing to radiate. The electron simply exists in its quantum state, stable, unchanging, persistent. Not because some force is preventing it from radiating, not because some rule is being broken or bent, but because the conditions required for radiation, classical acceleration of a charged particle, simply do not exist inside the quantum atom. The quantum description of the atom is not just a minor correction to the classical picture, it is a complete replacement. The classical atom, with its orbiting electrons and predictable trajectories, does not exist. It was a useful mental model for a brief period in the history of physics, but it is wrong. The true atom is a quantum object. Its electrons exist in standing wave states, described by wave functions, governed by the Schrödinger equation, and characterized by probabilities rather than certainties. And those states are stable. Absolutely, fundamentally, quantum mechanically stable. This is why your atoms do not collapse. This is why the matter in your body holds together. This is why the ground beneath your feet is solid. This is why chemistry works, why molecules form, why crystals grow, why stars burn, why planets hold together, why the universe is filled with stable structures made of atoms that have persisted for billions of years. Not because some mysterious force prevents collapse, but because the electron in a quantum stationary state is simply not the kind of thing that collapses. It is not a classical particle in an orbit. It is a quantum wave in a standing pattern. And standing waves do not spiral inward, they just stand. Stable, persistent, and enduring. But this raises the next question naturally. If electrons in stable quantum states do not radiate, if they just sit in their states indefinitely without emitting any energy at all, then how do atoms ever emit light? We know they do. The spectral lines that Bohr explained, the colors of neon signs, the glow of heated metals, the light from stars, all of this comes from atoms emitting photons. If electrons in stationary states never radiate, where does that light come from? The answer involves something we have not discussed yet: transitions. Quantum transitions between energy levels. And the physics of these transitions reveals something even more remarkable about how electrons exchange energy with the universe around them. So we have arrived at a picture that is beautiful and strange in equal measure. Electrons in atoms do not orbit the nucleus like tiny planets. They exist in quantum states, standing wave patterns described by wave functions spread out across space as probability clouds, inherently stable and persistent. As long as an electron remains in one of these stationary states, it does not radiate. It does not lose energy. It simply exists, unchanged, indefinitely. But this immediately raises a question that demands an answer. If electrons in stationary states never emit energy, then how does anything ever glow? How does a neon sign produce that vivid red-orange light? How does a campfire produce the warm yellow flicker you see on a summer night? How do stars shine? How does a hot piece of metal glow red, then orange, then white as it heats up? All of this light comes from atoms. All of it involves electrons emitting energy in the form of photons. If electrons in stable quantum states never radiate, where does all this light come from? The answer is one of the most important ideas in all of quantum physics. Electrons can change states. They can move from one allowed energy level to another. And when they do, they emit or absorb energy. Not continuously, not gradually, but in a single, discrete jump. All at once. One quantum state to another. Nothing in between. This is fundamentally different from anything in classical physics. In classical physics, energy changes are continuous. A ball rolling uphill slows down gradually, losing kinetic energy smoothly and continuously as it climbs. A pendulum swinging back and forth exchanges kinetic and potential energy in a smooth, flowing rhythm. A radio antenna emits electromagnetic radiation in a steady, continuous stream as electrons are pushed back and forth along the wire. Everything happens gradually. There are no jumps, no gaps, no sudden transitions from one state to another, with nothing in between. In quantum physics, the energy of an electron in an atom can only change by jumping from one allowed level to another. The electron cannot smoothly transition through intermediate energies because there are no intermediate energies. The allowed energy levels are discrete, like the rungs of a ladder. You can be on the first rung or the second rung, but you cannot be between them. There is no between. When the electron moves from a higher energy level to a lower one, it does not gradually lose energy along the way. It makes an instantaneous transition, disappearing from the higher state and appearing in the lower state, with no time spent at any energy in between. And the energy difference between the two states is released as a single photon, a single particle of light, carrying exactly that amount of energy. This is what produces the light you see from atoms. Every photon emitted by an atom is the result of an electron making a quantum transition from a higher energy state to a lower energy state. The photon carries away exactly the energy difference between the two states, not approximately, not roughly, exactly, to many decimal places of precision. The energy of the emitted photon equals the energy gap between the two quantum states involved in the transition. And because the energy levels are discrete, the energy differences between them are also discrete. Each possible transition produces a photon with a specific energy, which means a specific frequency, which means a specific wavelength, which means a specific color. This is why atoms emit light at specific colors rather than a continuous rainbow. When you heat hydrogen gas and look at its light through a prism or a spectrograph, you do not see a smooth spectrum of every color. You see a handful of sharp, bright lines at very specific wavelengths. A red line, a blue-green line, a blue-violet line, a few others in the ultraviolet. Each line corresponds to a specific transition between specific energy levels. The red line is produced when an electron drops from the third energy level to the second. The blue-green line comes from a drop from the fourth level to the second. The blue-violet line comes from the fifth to the second. Each transition produces one color and only that color. This pattern of spectral lines is unique to each element. Hydrogen has its pattern. Helium has a different pattern. Neon has its own. Sodium has its own. Every element has a unique set of allowed energy levels, which means a unique set of possible transitions, which means a unique spectral fingerprint. This fingerprint is so distinctive that it serves as an identity card for every element in the universe. You see the consequences of this everywhere, often without realizing it. The vivid orange glow of sodium street lamps, the kind that line highways and parking lots in many cities, is produced by a specific quantum transition in sodium atoms. Electrons in the sodium vapor are excited by the electrical discharge running through the lamp, bumped up to a higher energy state. When they drop back down, they emit photons at a wavelength of about 589 nanometers, which your eyes perceive as that distinctive deep orange. It is not a mixture of colors producing orange, it is a single, precise wavelength. One transition, one color. Every sodium street lamp on the planet glows that same shade of orange because the quantum energy levels of sodium are fixed by the laws of physics. They do not vary from atom to atom. Every sodium atom in the universe has exactly the same set of energy levels and produces exactly the same spectral lines. Astronomers exploit this universality to decode the cosmos. When they point a telescope at a distant star and spread its light into a spectrum, the pattern of bright and dark lines reveals exactly which elements are present in the star's atmosphere. Hydrogen lines tell them hydrogen is there. Helium lines reveal helium. Iron lines reveal iron. The specific wavelengths are unmistakable, as distinctive as a fingerprint. Astronomers can determine the chemical composition of a star that is hundreds or thousands of light years away without ever visiting it, without collecting a single sample, purely by reading the quantum fingerprints embedded in its light. They can do the same for the atmospheres of planets orbiting those stars, reading the spectral signatures of molecules like water vapor, carbon dioxide, and methane in the light that filters through an exoplanet's atmosphere. These are quantum transitions, the same physics that makes a neon sign glow, operating across billions of miles of space. The discrete nature of energy levels is not an abstract theoretical idea. It is the tool that allows us to read the composition of the universe. But electrons do not only emit photons, they can also absorb them. If a photon with exactly the right energy strikes an atom, an electron can absorb that photon and jump from a lower energy state to a higher one. The key word here is exactly. The photon must carry precisely the energy difference between the two states. Not a little more, not a little less. Exactly the right amount. If the photon's energy does not match any available transition, the atom simply will not absorb it. The photon passes through the atom as if it were not there. This is why glass is transparent to visible light. The energy levels in the atoms that make up glass are arranged so that no available transition corresponds to the energy of visible light photons. Visible light photons do not have the right energy to excite any electron in glass from one state to another, so they pass through without being absorbed. The glass is transparent because its atoms cannot use visible light. Ultraviolet light, on the other hand, has higher energy photons that do match certain transitions in glass, which is why glass blocks most ultraviolet light. And infrared light has lower energy photons that can be absorbed by certain vibrational modes of the glass molecules, which is why glass is partially opaque to some infrared wavelengths. Transparency and opacity, phenomena you encounter every day when you look through a window or feel the warmth of sunlight through a windshield, are direct consequences of quantum energy levels and the selectivity of quantum transitions. This selectivity is absolute. It is all or nothing. An electron either absorbs a photon of exactly the right energy and jumps to a higher state, or it does not absorb the photon at all. There is no partial absorption. There is no gradual excitation where the electron slowly climbs part way to a higher state. The transition either happens or it does not. This is radically different from classical physics, where a charged object can absorb any amount of energy from an electromagnetic field continuously and smoothly, regardless of the amount. Einstein understood this deeply. In 1905, the same year he published his theory of special relativity, he published a paper on the photoelectric effect that provided some of the earliest and most compelling evidence for the quantum nature of light. The photoelectric effect is a phenomenon where light shining on a metal surface ejects electrons from the surface. Classical physics could not explain it properly. According to classical wave theory, the energy delivered by light depends on its intensity, its brightness. Brighter light delivers more energy. So classical physics predicted that shining a very bright, dim red light on a metal should eventually knock electrons loose, because the accumulated energy from the bright light should build up until it is enough to free the electrons. And shining a very faint ultraviolet light should not eject electrons very effectively, because the faint light delivers less total energy. But experiments showed the opposite. No matter how bright the red light was, no matter how long you shone it on the metal, it never ejected electrons. The energy simply did not accumulate. And even very faint ultraviolet light ejected electrons immediately, as soon as it was turned on, with no delay. The brightness of the light affected how many electrons were ejected, but not whether any were ejected at all. That was determined entirely by the color of the light, its frequency. Below a certain frequency threshold, no electrons were emitted regardless of brightness. Above that threshold, electrons were emitted regardless of how faint the light was. Einstein explained this by proposing that light is not a continuous wave, but comes in discrete packets, quanta, each carrying an energy proportional to its frequency. Each photon carries a specific amount of energy. A red photon carries less energy than a blue photon. An ultraviolet photon carries more energy than either. When a photon strikes the metal surface, it interacts with a single electron, delivering all its energy to that one electron in a single quantum event. If the photon's energy is greater than the energy binding the electron to the metal, the electron is ejected. If the photon's energy is less than the binding energy, the electron is not ejected, no matter how many low-energy photons you fire at the surface. Each photon acts individually. You cannot combine the energy of two low-energy photons to eject one electron in normal photoelectric conditions. It is one photon, one interaction, all or nothing. This demonstrated that light itself is quantized. Energy is exchanged between light and matter in discrete chunks, not in smooth, continuous flows. The quantum nature of light and the quantum nature of atomic energy levels are two sides of the same coin. When an electron in an atom drops from a higher level to a lower level, it emits a single photon with exactly the energy difference. When a photon with exactly the right energy strikes an atom, it is absorbed entirely, and an electron jumps to a higher level. These are quantum transitions, discrete, instantaneous, all-or-nothing events that have no classical analogue. Now, there are different ways these transitions can happen, and understanding them reveals more about how electrons exchange energy with the universe. When an electron in a higher energy state drops to a lower energy state on its own, without any external trigger, this is called spontaneous emission. The electron simply drops. A photon is released. No one pushed the electron. No external field forced it down. It just happened. This might sound strange. If the electron is in a stable quantum state, why would it spontaneously drop to a lower state? The answer involves the quantum nature of the electromagnetic field itself. Even in a perfect vacuum, the electromagnetic field has quantum fluctuations, tiny random oscillations in the field's energy due to the Heisenberg uncertainty principle. These fluctuations are always present, even when no photons are explicitly around. The vacuum is not truly empty. It buzzes with the minimal residual energy that the uncertainty principle requires. These vacuum fluctuations can interact with the electron in a higher energy state and trigger a transition to a lower state, accompanied by the emission of a photon. Spontaneous emission is not truly spontaneous, in the sense of having no cause. It is triggered by the quantum vacuum itself. But there is an important detail. Spontaneous emission has a probability associated with it, not a certainty. An electron in an excited state does not drop immediately. It drops randomly, with a characteristic average lifetime that depends on the specific transition involved. Some transitions happen quickly, with average lifetimes of a few billionths of a second. Others take much longer. Some are extremely unlikely and take hours, days, or even years on average. The mathematics of quantum mechanics gives precise predictions for these lifetimes, and they match experimental measurements beautifully. There is also stimulated emission. This occurs when a photon with exactly the right energy passes near an atom whose electron is in an excited state. The passing photon can trigger the electron to drop to a lower state, emitting a second photon that is identical to the first. Same energy, same frequency, same direction, same phase. Two photons come out where one went in. Both have exactly the same properties. This process, stimulated emission, is the fundamental mechanism behind the laser. The word laser is an acronym for Light Amplification by Stimulated Emission of Radiation. A laser works by creating a population of atoms with electrons in excited states, and then stimulating them to emit photons in a cascade. Each emitted photon triggers more emissions, producing a beam of light where all the photons are identical, coherent, marching in perfect lockstep. Laser light is a direct technological application of quantum transitions between energy levels. And then there is absorption, which we have already discussed. A photon with exactly the right energy is absorbed by an atom, and an electron jumps from a lower state to a higher state. The photon is destroyed in the process, its energy converted into the electron's increased quantum energy. Emission and absorption are inverse processes. In emission, an electron drops and a photon is created. In absorption, a photon is destroyed and an electron rises. In both cases, the energy exchange is exact, discrete, and involves a quantum transition between allowed energy levels. These three processes, spontaneous emission, stimulated emission, and absorption, account for virtually all the ways electrons in atoms exchange energy with light. Every neon sign, every laser pointer, every star in the sky, every warm object radiating infrared light, all of it comes down to these quantum transitions. And every single one of them involves a discrete jump between allowed energy levels, with a photon carrying exactly the energy difference. Now, there is a crucial distinction that needs to be made here, and it is one of the most important clarifications in this entire story. Everything we have discussed so far applies to bound electrons. Electrons that are part of an atom, held by the electrical attraction to a nucleus, occupying specific quantum energy levels. These bound electrons do not continuously radiate. They emit or absorb energy only through discrete quantum transitions. This is the resolution to the crisis of atomic stability. But this does not mean that electrons can never continuously radiate. They can. The key is the distinction between bound electrons in atoms and free electrons that are being accelerated by external forces. A free electron, one that is not bound to any atom, can be accelerated by electric or magnetic fields, and when it is accelerated, it does radiate electromagnetic energy, exactly as Maxwell's equations predict. The classical rule that accelerating charges radiate is not wrong. It is completely correct. It has been confirmed by countless experiments. It applies every time a charge is genuinely accelerated in the classical sense. Think back to the examples from earlier in our story. The synchrotron light sources, where electrons are steered around curved paths at nearly the speed of light and radiate so intensely that entire research facilities are built around the light they produce. The X-ray tubes in hospitals, where electrons slam into metal targets and emit Bremsstrahlung as they decelerate. The radio antennas that produce every wireless signal on the planet by pushing electrons back and forth along a wire. In every single one of those cases, charges are genuinely accelerating in the classical sense, following curved paths, decelerating against targets, oscillating back and forth. And they radiate exactly as Maxwell's equations demand. The classical rule is alive and well. It works perfectly for free charges being driven by external forces, and you do not need a laboratory to see it. Nature produces classical radiation from accelerating charges on scales both intimate and vast. When a bolt of lightning tears through the atmosphere, the enormous electrical discharge accelerates free electrons violently through the air. Those accelerating charges radiate electromagnetic waves across a broad spectrum. This is why lightning produces a brilliant flash of visible light, but it does not stop there. Lightning also generates radio waves, the same kind of electromagnetic radiation that carries your favorite broadcast, except produced by the raw violence of a 100 million volt discharge rather than the controlled oscillation of an antenna. You can actually hear these radio waves as the static crackle on an AM radio during a thunderstorm. Every pop and sizzle in that static is the electromagnetic signature of charges accelerating in a plasma channel that reaches temperatures of roughly 30,000 degrees, 5 times hotter than the surface of the Sun. Each bolt lasts only a fraction of a second, but during that fraction of a second, the electrons in the discharge are accelerating so violently that they broadcast across the electromagnetic spectrum, from radio frequencies all the way up to X-rays. Maxwell's equations playing out in real time in the sky above your head. Even in space, the principle operates on vast scales. Earth is surrounded by radiation belts, enormous donut-shaped regions of space where charged particles, mostly electrons and protons stripped from the solar wind, are trapped by Earth's magnetic field. These particles do not sit still. They spiral along the curved magnetic field lines, tracing helical paths through space. A charged particle spiraling along a curved path is accelerating, and it radiates. The radiation emitted by these spiraling electrons has been detected and studied by spacecraft for decades. It tells scientists about the density and energy of the trapped particles, about the strength and shape of Earth's magnetic field, about the dynamics of the space environment surrounding our planet. This radiation is purely classical. Free charges accelerating along curved paths and emitting electromagnetic waves, exactly as Maxwell described over a century and a half ago. And then there is the aurora borealis, the northern lights. When solar wind particles slam into Earth's magnetic field during a geomagnetic storm, some are funneled down along the field lines toward the poles. As they accelerate along these curved paths and plunge into the upper atmosphere, two things happen simultaneously. The charged particles radiate as they accelerate, classical radiation from classical acceleration. And when they collide with atoms of oxygen and nitrogen in the atmosphere, they excite those atoms, bumping electrons into higher quantum states. When those excited electrons drop back down to lower states, they emit photons at specific wavelengths determined by the quantum energy levels of the atoms involved. The green glow that dominates most auroral displays comes from a specific quantum transition in oxygen atoms. The red and purple hues come from different transitions in oxygen and nitrogen at different altitudes. Accelerating charges and quantum transitions working side by side in the same sky, producing one of nature's most spectacular light shows. Classical radiation and quantum emission, both real, both operating by their own rules, both visible to anyone who looks up on a clear night near the poles. So the classical rule is not wrong. It is simply misapplied when people try to use it to describe electrons inside atoms. A bound electron in a quantum stationary state is not a free electron being shoved around by an external field. It is not tracing a curved path. It is not accelerating. It is existing in a quantum state, a standing wave pattern, a probability cloud. The conditions required for classical radiation, genuine classical acceleration of a charged particle, simply do not exist for bound electrons in stationary states. The rule about accelerating charges radiating still applies. It just does not apply to that situation, because that situation does not involve classical acceleration. This distinction matters enormously for understanding the title question. Why does an electron never run out of energy? The answer depends on which electron you are talking about and what circumstances it is in. A bound electron in a stable quantum state does not radiate because it is not accelerating. It does not need fuel because it is not expending energy. It just exists in its quantum state. A free electron being pushed around by external forces absolutely does radiate and does lose energy, exactly as classical physics predicts. But that is a different situation entirely. The electron is not bound to an atom. It is not in a quantum stationary state. It is being forced to accelerate by an external field, and the energy it radiates comes from the field that is pushing it. The electron itself is not draining some internal reserve. The energy comes from outside. There is another common misconception worth addressing. People sometimes imagine that the electron chooses when to emit a photon, as if it has some kind of agency or decision-making ability. It does not. The electron does not choose anything. The physics of the quantum state determines everything. Whether a transition can happen, how likely it is, what energy the emitted photon will have, all of this is determined by the mathematics of quantum mechanics. The Schrödinger equation, combined with the rules of quantum electrodynamics, gives precise probabilities for every possible transition. The electron does not decide to drop from one level to another. The quantum state evolves according to the equation, and if conditions are right, a transition occurs with a certain probability. It is physics, not choice. Similarly, the electron does not know what energy photon to emit. The energy of the emitted photon is determined entirely by the energy difference between the initial and final states. There is no decision process, no information processing, no awareness on the part of the electron. The photon's energy is fixed by the laws of quantum mechanics and the structure of the atom. The electron has no more choice in the matter than a ball has a choice about which way to roll when you place it on a slope. The physics determines the outcome. The electron just follows the rules. Now, let us connect all of this back to the central question. Atoms emit light. That is obvious. The sky is full of glowing stars. Your room is lit by LED bulbs that operate by quantum transitions in semiconductor materials. Neon signs glow. Flames have color. The universe is ablaze with photons produced by electrons changing energy levels. But all of this light comes from transitions, from electrons jumping from higher states to lower states. It does not come from electrons slowly, continuously bleeding away their energy while sitting in a stable state. The radiation is discrete. It happens in quantum jumps. And between those jumps, while the electron sits in its stationary state, nothing is emitted. Nothing at all. The electron is perfectly stable, perfectly quiet, radiating nothing, losing nothing, until some interaction, a collision with another atom, the absorption of a photon, the influence of the quantum vacuum, triggers a transition to a different state. And once the electron reaches its lowest possible state, the ground state, even those discrete transitions stop, because there is no lower state to transition to. There is nowhere further to fall. The electron in the ground state of hydrogen cannot emit a photon and drop to a still lower level, because no such level exists. The ground state is the bottom of the ladder, the last rung, the absolute minimum energy the electron can have while remaining bound to the atom. And so the electron sits in the ground state indefinitely, radiating nothing, losing nothing, stable and unchanging, for as long as the atom itself exists. The stability of matter, the fact that atoms do not collapse, the fact that everything around you holds together, comes down to this. Electrons in atoms occupy quantum states. In those states, they do not radiate continuously. They exchange energy only through discrete quantum transitions. And there is a lowest state, a ground state, below which they cannot fall. Once an electron reaches the ground state, it stays there. Not because something prevents it from radiating, not because some force holds it in place, but because the quantum rules of nature simply do not permit any further loss of energy. The ground state is the end of the line. We have now arrived at the heart of the question. The electron in an atom does not continuously radiate. It occupies quantum states, stationary standing wave patterns that are inherently stable. It exchanges energy only through discrete quantum transitions, jumping between allowed energy levels. All of this explains why atoms do not collapse the way classical physics predicted. But it does not yet explain the deepest layer of the answer. Why does the electron never run out of energy entirely? Why does it not keep making transitions, dropping lower and lower and lower, emitting photon after photon, until all its energy is gone and it finally crashes into the nucleus? What stops that process? What prevents the electron from falling all the way down? The answer is the ground state. And understanding the ground state, truly understanding why it exists and what it means, answers the title question completely. Every quantum system has a ground state. It is the lowest possible energy level the system can occupy. For an electron bound to a hydrogen nucleus, the ground state is the state labeled n equals 1 in the quantum mechanical description. It is the smallest, most tightly bound standing wave pattern the electron can form around the nucleus. And it has a specific, calculable energy. In hydrogen, the ground state energy is negative 13.6 electron volts. That negative sign means the electron is bound. It would take 13.6 electron volts of energy to rip the electron completely free from the atom, to ionize it, to send it off into space as a free particle. The ground state is not zero energy. This is a critical point that many people misunderstand. The electron in the ground state still has energy. It has kinetic energy from the quantum mechanical structure of its wave function. It has potential energy from its electrical attraction to the nucleus. The total energy is the sum of these two contributions, and that sum is the ground state energy. What makes the ground state special is not that the electron has zero energy, it is that the electron has the minimum possible energy. There is no lower state, no rung beneath this one on the ladder. The electron cannot emit a photon and drop to a still lower level because the mathematics of the Schrödinger equation simply does not permit any solution with lower energy for this system. The ground state is the bottom, the absolute floor. And this is the ultimate reason atoms are stable. An electron in the ground state cannot lose any more energy. It cannot radiate a photon because there is no lower state to transition to. The only way an electron emits a photon is by dropping from a higher state to a lower state. If there is no lower state, there is no transition. If there is no transition, there is no photon. If there is no photon, there is no energy loss. The electron simply sits in the ground state, stable, unchanging, radiating nothing, losing nothing, for as long as the atom exists. But why does the ground state exist? Why can the electron not just keep falling closer and closer to the nucleus, with lower and lower energy, spiraling all the way down to zero distance? What prevents the electron from collapsing onto the nucleus the way classical physics predicted? This is where the Heisenberg uncertainty principle enters the story and provides one of the deepest explanations in all of physics. The uncertainty principle, formulated by Werner Heisenberg in 1927, states that certain pairs of physical properties cannot both be known precisely at the same time. The most famous pair is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving, and vice versa. This is not a limitation of our instruments. It is not that our measuring devices are too crude. It is a fundamental property of nature. The particle literally does not have both a precise position and a precise momentum simultaneously. These properties are inherently uncertain, inherently fuzzy, built into the fabric of quantum mechanics. Now apply this to an electron near a nucleus. Imagine trying to confine the electron closer and closer to the nucleus. As you squeeze the electron into a smaller and smaller region of space, you are reducing the uncertainty in its position. You know more precisely where the electron is. But the uncertainty principle says that as the position uncertainty decreases, the momentum uncertainty must increase. The electron's momentum becomes more and more uncertain, which means it can have larger and larger values of momentum. Larger momentum means larger kinetic energy. So as you try to push the electron closer to the nucleus, its kinetic energy increases. Think about this carefully, because it is the key to everything. Bringing the electron closer to the nucleus reduces its potential energy. The electrical attraction between the negative electron and the positive nucleus is stronger at shorter distances, so the potential energy becomes more negative, which is favorable. This is the force pulling the electron inward, the electrical attraction that classical physics says should cause the electron to spiral all the way in. But at the same time, confining the electron to a smaller space increases its kinetic energy due to the uncertainty principle. This is a quantum mechanical effect with no classical analogue. It is not a force in the traditional sense. It is a consequence of the wave nature of the electron. Waves confined to smaller spaces must have shorter wavelengths, which means higher frequencies, which means higher energy. This is the same principle that makes the pitch of a guitar string go up when you shorten the vibrating length. Shorter confinement means higher energy. So there are two competing effects. Bringing the electron closer to the nucleus lowers its potential energy, but raises its kinetic energy. Moving it farther from the nucleus lowers its kinetic energy, but raises its potential energy. The ground state is the perfect balance point. It is the configuration where the total energy, kinetic plus potential, is at its absolute minimum. Any attempt to push the electron closer to the nucleus would increase the kinetic energy by more than it decreases the potential energy, resulting in a net increase in total energy. Any attempt to pull the electron farther from the nucleus would increase the potential energy by more than it decreases the kinetic energy, again resulting in a net increase. The ground state is a natural equilibrium, a minimum in the total energy landscape. This is why the electron does not collapse into the nucleus. It is not that some mysterious force pushes the electron back out. It is that the uncertainty principle makes collapse energetically impossible. Squeezing the electron down to the nucleus would require confining it to a region roughly the size of the nucleus, about 100,000 times smaller than the atom. This extreme confinement would produce such enormous momentum uncertainty, and therefore such enormous kinetic energy, that the total energy would skyrocket far above the ground state energy. Collapse is not energetically favorable. It costs more energy than it saves. The atom is stable because the ground state represents the lowest total energy, and that lowest energy corresponds to the electron being spread out over a region much larger than the nucleus, not collapsed onto it. Let me put some numbers to this to show how it works. The hydrogen atom has a ground state radius of about 0.53 angstroms, or about 53 trillionths of a meter. The hydrogen nucleus, a single proton, has a radius of about 0.88 femtometers, roughly 100,000 times smaller. If you tried to confine the electron to a region the size of the proton, the uncertainty principle would require the electron's momentum to be so large that its kinetic energy would be on the order of hundreds of millions of electron volts. The ground state energy of hydrogen is only 13.6 electron volts. Forcing the electron onto the nucleus would require millions of times more energy than the electron currently has. It is simply not going to happen under ordinary circumstances. The math forbids it. The physics forbids it. Nature forbids it. This minimum energy that the electron retains even in the ground state is sometimes called zero-point energy. It is the energy that remains even when the system is in its lowest possible state, when it cannot lose any more energy, when it is as cold and as quiet as the laws of physics allow. Zero-point energy is a direct consequence of the uncertainty principle. Because you cannot simultaneously reduce both the position uncertainty and the momentum uncertainty to zero, the electron cannot have zero kinetic energy while also being localized near the nucleus. There is always some residual energy, some quantum mechanical buzz, some irreducible minimum. This zero-point energy is not thermal energy. It has nothing to do with temperature. Even at absolute zero, even if you cooled the atom to the lowest temperature physically possible, the electron would still have its zero-point energy. You cannot extract it. You cannot remove it. It is the price nature charges for confining a quantum particle to a finite region of space. Now we can finally address the title question directly and completely. An electron never runs out of energy. Why not? The question itself contains a hidden assumption, and that assumption is wrong.
The question implies that the electron is using energy, spending energy, consuming energy, the way a battery uses its stored charge, or the way a car engine burns fuel. It implies that the electron needs a power source to keep going, that it is somehow actively doing something that requires energy input, and that without that input, it should eventually stop. But the electron is not using energy. It is not spending anything. It is not burning fuel. It is not powering any process. An electron in a stable quantum state is simply existing. That is all. It occupies its quantum state. Its wave function sits there, a standing wave pattern, a probability distribution that does not change with time. Nothing is being consumed. Nothing is being expended. There is no process that requires an ongoing supply of energy. This is where the battery analogy completely breaks down. A battery stores chemical energy and releases it gradually through chemical reactions that drive current through a circuit. The battery runs down because the chemical reactions consume the reactive chemicals. Eventually, the reactants are used up and the battery dies. The battery is actively doing something. It is converting chemical energy to electrical energy. It is performing work. And performing work requires a supply of energy that eventually runs out. The electron in an atom is doing none of this. It is not converting one form of energy into another. It is not performing work. It is not driving a current. It is not pushing anything. It is not pulling anything. It is simply sitting in a quantum state, existing. The state is stationary. Nothing changes. No energy flows in. No energy flows out. The electron is in equilibrium, balanced at the minimum energy configuration permitted by the laws of quantum mechanics. Think of it this way. A ball sitting at the bottom of a valley does not need fuel to stay there. It is already at the lowest point. Gravity pulled it down, and now it sits at rest. No energy is required to maintain its position. It will sit there forever unless something comes along and kicks it out. The ball is not doing anything. It is just sitting at the bottom of the valley. The electron in the ground state is similar, though the analogy is imperfect because the electron is a quantum object, not a classical ball. The electron is in the lowest energy state. It has nowhere lower to go. No energy is required to maintain this state because maintaining it costs nothing. The electron is not fighting against any force that would push it out. It is not resisting collapse. It is simply at the bottom, the quantum mechanical bottom, the ground state. No fuel is needed because no fuel is being consumed. No energy supply is required because no energy is being spent. The electron is not like a satellite that needs occasional boosts to maintain its orbit, or a car that needs gasoline to keep its engine running, or a light bulb that needs electricity to keep glowing. Those systems are all actively converting energy from one form to another. They are doing work. The electron in the ground state is doing no work. It is performing no function that requires an energy input. It is simply being. And this state persists indefinitely. Not for a long time, not for billions of years, though atoms have been stable for billions of years and their electrons have been in ground states for that entire time. The state persists indefinitely because there is no mechanism by which it can change on its own. An electron in the ground state can only change its state if something external happens to it. If a photon with the right energy comes along and is absorbed, the electron can jump to a higher state. If the atom collides with another atom or particle with enough energy, the electron can be excited or even knocked free. But these are all external events. They require energy input from outside the atom.
Left entirely alone, with nothing interacting with it, the electron in the ground state will remain there forever. Not because some magical force holds it in place, but because the quantum rules of nature provide no pathway for it to go anywhere else without external energy. This is the profound truth behind the stability of matter. Every atom you have ever encountered, every atom in your body, every atom in the earth beneath you, every atom in the stars above you, owes its stability to the existence of the ground state. The ground state is the reason atoms do not collapse. The ground state is the reason matter holds together. The ground state is the reason chemistry is possible, because chemistry depends on atoms being stable objects that can bond with each other in predictable ways. The ground state is the reason you exist. Consider what the universe would be like without this principle. If electrons could fall to arbitrarily low energies, if there were no ground state, if the quantum energy ladder extended downward without limit, every electron in every atom would radiate photon after photon, falling lower and lower, emitting an infinite cascade of radiation as it dropped through an infinite number of energy levels. Atoms would shrink without limit. Matter would collapse. No stable structures could form. No molecules, no crystals, no cells, no organisms, no planets, no stars. The universe would be a featureless sea of collapsed nuclei and radiation, with no structure, no complexity, no chemistry, and certainly no life. Everything we see, everything we are, everything we have ever known or experienced exists because quantum mechanics provides a floor, a ground state, a minimum energy below which electrons cannot fall. The implications extend far beyond individual atoms. When atoms bond together to form molecules, the electrons rearrange themselves into new quantum states, molecular orbitals that span multiple nuclei. These molecular orbitals also have ground states, minimum energy configurations that are stable and persistent. The covalent bonds holding molecules together, the hydrogen bonds that give water its remarkable properties, the complex folding patterns of proteins, the double helix of DNA, all of these structures are stable because the electrons within them occupy quantum states with well-defined ground states. The chemistry of life depends entirely on the stability of these quantum states. When atoms come together in vast numbers to form solid materials, the quantum states of the electrons merge into energy bands, continuous ranges of allowed energies that determine whether a material is a metal, a semiconductor, or an insulator. The electrons fill these bands from the bottom up, occupying the lowest available states first, each electron settling into its quantum state without radiating, without losing energy, without decaying. The structural integrity of every solid object you have ever touched, every bridge, every building, every grain of sand, every bone in your body, depends on electrons occupying stable quantum states in these energy bands. Even the stars owe their existence to this principle. A star is a massive ball of plasma, mostly hydrogen and helium, held together by gravity. At the enormous temperatures and pressures inside a star, atoms are ionized, their electrons stripped away, and nuclear fusion converts hydrogen into helium, releasing vast amounts of energy. But the star itself, the structure that holds together for billions of years, burning steadily and reliably, depends on quantum mechanical principles governing the behavior of particles under extreme conditions. And when a star like our Sun eventually exhausts its nuclear fuel,
billions of years from now, it will collapse into a white dwarf, a dense remnant about the size of Earth, but with the mass of a star. What prevents the white dwarf from collapsing further?
Electron degeneracy pressure, a quantum mechanical effect closely related to the Pauli exclusion principle, which itself is connected to the fundamental quantum nature of electrons. Wolfgang Pauli showed that no two electrons can occupy the same quantum state simultaneously. In a white dwarf, the electrons are packed so tightly that they fill all the lowest available quantum states. They cannot be compressed further because there are no lower states available. The quantum mechanical flaw, the same principle that prevents an electron in a hydrogen atom from collapsing into the nucleus, prevents an entire dead star from collapsing under its own gravity. The same physics operates at the scale of a single atom and at the scale of a stellar remnant containing as much mass as the Sun. Let me be precise about what we are not saying. We are not saying that electrons have infinite energy. They do not. The ground state of hydrogen has a specific, finite energy. We are not saying that electrons never lose energy under any circumstances. They clearly do. Electrons in excited states drop to lower states and emit photons. Free electrons being accelerated by external fields radiate energy. Electrons in atoms can be kicked out entirely if hit with enough energy. Electrons exchange energy with their surroundings all the time, through absorption, emission, collisions, and other interactions. What we are saying is that an electron in the ground state of an atom, the lowest allowed quantum state, does not lose energy because it has no lower state to transition to. It does not need fuel because it is not consuming energy. It is not a perpetual motion machine because it is not a machine at all. It is not doing anything. It is simply existing in the lowest state permitted by quantum mechanics. And that state is permanent. Not approximately permanent, not stable for a very long time. Permanent in the deepest sense physics can offer. The ground state of hydrogen has been the same since the first hydrogen atoms formed in the early universe, roughly 380,000 years after the Big Bang, when the cosmos cooled enough for protons and electrons to combine. Those atoms, and the countless trillions upon trillions of hydrogen atoms that have existed since, all had ground state electrons sitting quietly in the same quantum state, with the same energy, the same wave function shape, the same probability distribution. For over 13 billion years, without any fuel, without any energy input, without any maintenance, without any sign of decay or degradation. The ground state does not wear out. It does not age. It does not slowly degrade over time. It is a fixed property of the quantum system, as unchanging as the laws of physics themselves. This is the answer. An electron never runs out of energy because it was never spending energy in the first place. It is not a battery slowly draining. It is not an engine burning fuel. It is not a spinning top gradually losing momentum to friction. It is a quantum object in its lowest allowed state, a state that is stable not because something holds it there, but because the laws of quantum mechanics provide no mechanism for it to go any lower. The ground state is the floor of reality. Below it, there is nothing. No lower rung, no deeper level, no further descent. The electron sits at the bottom, and the bottom is permanent. The next time you look at your hand, at the seemingly solid, stable matter that makes up your skin and bones and blood, remember what is happening at the atomic level. Trillions upon trillions of electrons, each one sitting in a quantum state, each one a standing wave of probability, each one stable and persistent, each one requiring no fuel, no power, no external supply of energy to maintain its existence. These electrons have been doing this for billions of years, ever since the atoms in your body were forged in the cores of ancient stars that lived and died long before our sun was born. The iron in your blood, the calcium in your bones, the carbon in every cell, all of it was assembled from atoms whose electrons have occupied stable quantum states since the moment those atoms were created in stellar furnaces
and supernova explosions billions of years ago. You are held together by quantum mechanics. The stability of your body, the structure of every molecule within you, the integrity of every cell, all of it depends on the fact that electrons in atoms occupy stable quantum states, and that those states have a ground level below which they cannot fall. If this were not true, if the ground state did not exist, if quantum mechanics did not provide this floor, you would not exist. Nothing would exist. The universe would be a structureless void. But quantum mechanics does provide that floor. The ground state is real, the stability is real, and every atom in the cosmos, from the hydrogen drifting in the vast emptiness between galaxies to the complex organic molecules in the cells of your brain, every single one of them is held together by this simple, profound, beautiful truth. The electron is not a battery. It does not run down. It does not need to be recharged. It is a quantum object in its lowest state, and that state is forever.